Okay, so in this video, I'm just going to walk you through a proof of mathematical induction to prove that this equation that we found in the last video for S sub n is a solution to this recurrence equation. So I'm just going to start this out by writing proof. You should always write proof to kind of indicate to the reader that you're starting a proof, and you can also add a note as to what type of proof you're doing. So in this case, we're doing a proof by induction, so I'm going to add that note there. And so the first case we want to consider, we want to say suppose n equals 1. Or sorry, that's a habit I fall into because normally we start proof by induction with the first case, but in this case our first term is 0. So actually starting with the 0th case. Suppose n equals 0. Then s sub 0 equals 2 times 0 squared plus 7 times 0. This is all 0, right? So that's 0. And our initial condition is s sub 0 equals 0. So that's what we wanted. Boom, we're good. Now this second case, or the second step, is the main part of the proof, right? We're going to suppose n equals k, and assume, right, that it's true that s sub k equals 2k squared plus 7k is a solution to s sub k equals s sub k minus 1 plus 4k plus 5, given the initial condition s sub 0 equals 0. And now that we've assumed this k case, we want to prove that the k plus 1 case is true whenever we assume that the k case is true. So we actually may want to add here that suppose n equals k for some k in the natural numbers, because we want this to be any k, really, right? We want to prove that we can pick any k and prove that the next term is true. So now that we've supposed n equals k, we want to suppose n equals k plus 1, right? And so now we're looking at the k plus 1 term, and we know from our recurrence relation that s sub k plus 1 is going to equal s sub k plus 4k plus 5. So if we suppose n equals k plus 1, we don't do what I did and make a silly mistake, right? This is s sub k plus 4 times k plus 1 plus 5, right? Because we're taking this equation up here and we're putting k plus 1's in. So this is an s sub k plus 1, this is an s sub k, this is a k plus 1. So we still want this piece here, right? So we're gonna substitute s sub k in again. This is 2k squared plus 7k, and we're gonna distribute this so it's 4k plus 4 plus 5. And so we're just gonna pull out this piece here that we want. So we're gonna pull out 2k squared plus 4k plus 2, and that's gonna leave us with just 7k plus 7, right? Because we have 9 here, but we're going to take 2 over there, right? And over here in our scratch work, we agreed that these are equal, right? So this is just 2 times k plus 1 squared plus, and then hey, look what we have here. We have a 7k plus 7. We pull a 7 out of that. That's k plus 1. That's exactly what we wanted, right? And so then we just say, therefore, because of 1, our initial condition, and 2, our inductive stuff, and by the principle of mathematical induction, s sub n equals 2n squared plus 7n is a solution to s sub n equals s sub n minus 1 plus 4n plus 5 for the initial condition s sub 0 equals 0.